Okay, this is it. This is a metallic rectangle. I want to talk about metallic rectangle in this video. Uh, okay, so let us now start by kind of definition. Definition here. So suppose you have a rectangle like this. So if this is the length and the width, so by definition, a metallic rectangle is a rectangle such that the length to width, that ratio is equal to metallic ratio. So we give mu n equal to half of n plus square root n square plus 4. Okay, so I'm going to deal with some special case with n equal to 1. So we will have what we call golden rectangle, golden rectangle. Okay, for n equal to 2, we're gonna have what we call silver ratio, silver rectangle, sorry. And for n equal to 3, so in literature and from history we call them bronze rectangle. Okay, so now some properties. It is about this relation, but another property is that some rectangles can also be constructed by using the conjugate of this one. So the conjugate of silver ratio, which is a half of n minus square root n square plus 4. So we know that this one is negative. So which means that a multiple of its opposite will also play a role in construction also of the metallic rectangle. So remember this is positive. So now starting with golden ratio, so we can get some rectangle. So we talk about the first one, golden rectangle, golden rectangle. Okay, so how to construct it? Geometrically, you take a square like width and a square. So now from a square we get a half of it, x over 2, x over 2. So take some half, project in the corner. So on this direction, you take an arc length of the circle from center here. So you can draw an arc length, and here you can raise up this side. This is it, and we are going to prove that this side. So we are going to prove that this side is negative x times the conjugate of the golden ratio. So we are in case n is equal to 1. Okay. So now the whole length, we are going to prove that the whole length is equal to x times z, so the width times the golden ratio, so that the ratio is equal to the golden ratio in case, of course, n equal to 1. Now we have to prove this. To prove it, let us take this like this diagonal from this corner. We take half of it. So we're gonna have the diagonal by using the Pythagorean theorem. Gonna have to raise power 2 plus now this width is x and we take square root. Now as it is the same length here, so on the other side, so this is z x over 2 plus z. Okay, this is after writing correctly, it is half of x over 2 times the square root of 5. So this is 4 plus 1 x square, it is 5x square, and then x square out over 4, it is x over 2 times square root 5. Okay, so now calculate. First prove this identity. First I have to prove this relation, and next we are going to prove finally, if you know the value of z, it is simple to prove that the length is equal to that one, and by doing so, we are proving that length over width is equal to the metallic ratio. Okay, so z here is equal to this on the other side, square root 5. This is exactly negative x half minus square root of 5 over 2. And that is exactly the metallic ratio, the conjugate of the metallic ratio with n equal to 1, as we have indicated. Okay, so next, this one is relation, is proof. Next, we can use this value of z, and we can plug in the expression of this length in order to prove this this identity. Okay, so what you have here is so it is equal to x plus z in order to get the length, and it is x plus or minus x plus half minus square root 5 over 2. So this is a common denominator 2x over 2 minus x. So distribute plus x squared root 5 over 2. So now we are going to get x out. So 2 minus 1 is 1, 1 plus the square root 5 over 2. And that is exactly the metallic ratio with n equal to 1. So that one is proved. This relation is also proved. And what it means is that this length of this rectangle we divide by the width, it is clearly equal to the it is equal to exactly this value 1 plus square root 5 over 2, which is the golden ratio. Okay, so but also this is golden rectangle, but also it can be proved that this rectangle here, this small one, is also a rectangle. It is golden if we set the width like W1, the length like L1. So with L1 equal to X and W1 equal to Z. And if we make this ratio length over width, also length over width. So finally, if we calculate, we prove that it is equal to the golden ratio after calculation. Okay, so now let us look at now the for n equal to 2, how we proceed. Okay, for n equal to 2, most of the time we call that a rectangle, silver rectangle. For this silver rectangle, okay, so we construct two squares of same size, and then from this we can take half of this part, and then on this direction we can rotate from the center here, half here, we rotate to find this arc, and we raise this one to form the whole rectangle here. So this diagonal, we can calculate it. So we are going to prove that this length, the length here, which if this part is z, it is going to be equal to, we are going to prove it is x times the silver ratio times x, and the width we don't need to prove it, but this z is going to be equal to negative x times the conjugate. This conjugate is negative. When you change sign multiplied by x, you get this length here. Okay, so now first of all, let us prove that z is equal to this value. So what you have to do is to take d, this diagonal, minus x. Okay, so what we have got to do is the square root of x square plus x square. Okay, this is d, so we have to remove length x. So this becomes twice x square, remove x. So we're gonna have a factor out x square out is x square root 2 minus x, this is and factor x out, we have this one. Now it is clear that this is the opposite of the silver ratio. If I start by negative x, you're gonna have 1 minus square root 2, and that is exactly, and this is exactly the silver ratio with n equal to 2. This is 1 minus square root 2 when n is equal to 2, as it is the case we are dealing with here. Now, next, as we have, so this value is verified, this relation is verified. So now we need to verify the first one. Okay, so let us do it over here again. Let us use this, and how to find, to prove this relation. So L is equal to, okay, L is equal to twice x plus z. So this is 2x plus z. So this is z. 2x minus x mu n. So mu n negative with n equal to 2. So this is 2x minus x. We have so we have square root of 2 minus 1. No, 1, the conjugate, sorry. This is negative the conjugate. Now, if negative 1 I factor it out, I have a mu n which is 1 minus square root 2. Okay. Now, if I distribute 2x minus x minus now plus x square root 2. So if I do so, what I get is 2x minus 1x is x plus x square root 2. So this is, I factor out x 1 plus square root 2. So now this is exactly the silver ratio with n equal to 2. This is 1 square root 2 with n equal to 2. So we have come to the end of this, the proof of the length being equal to this with n equal to 2. Okay, so now with n equal to 3, we are going to get similar result. Let us do it very quickly. Of course, we can also prove that if we set this being the width, number 1, new width, this we set it to new length. So also we can see that the ratio is equal to L1, W1 is equal to the silver ratio, which is 1 plus square root of 2. So which is exactly equal to L, this length, this one, over x. Okay. So similarly, with n equal to 3, we get same result. So we have n equal to 3, n equal to 3, we have bronze rectangle, so let us use now this 3, 1, 2, 3, x, x, x. So now, so in order to get the length, so we can project, take a half of this, half is somewhere here, so this is 3x over 2, this is 3x over 2, and then we project this one here. You are going to make a circle center here, and where it will fall, let us call it Z. You get a rectangle here. Okay, we can also prove that this rectangle is a bronze rectangle, like it is the case for this big rectangle here, with the width here and the whole value being the length. Okay, first of all, we show that the length is x times metric ratio with, of course, n equal to 3. That is what you have said. Next, okay, next we are also supposed to prove that z is equal to negative x times the conjugate n minus. Okay, mu n minus. Okay, in this case, in order to prove this one, we start by this, and with this one, with n equal to 3. So z here is equal to ZD is equal to this diameter, the diagonal, so D minus 3x, 3 half x, 3 half x. Okay, so now what is this? From Pythagorean, this is 3x over 2 power 2 plus this side, it must be, this must be x. Okay, because this is a square, this is a square, this is a square, 3 squares, and then we add additional metallic rectangle, which will also be the same. So in this case, let us continue here. X, this is x, like this, square. Now I take square root minus 3x over 2. Now here we get 9x square plus our common denominator will be 4. Here will be 4x square minus 3x over 2. Now it's gonna be equal. I can factor out x now, and I get square root of 13x square. X square has been factored toward over now 2. If I need to factor out 4 out of square root becomes 2. So now I have this square root. Okay, now we move 3x over 2. So we put on a common denominator, which is 2. And then we have x square root 13 minus 3x. Now I can factor x out, get x times 0. So if I factor negative in order to compare with this, I'm gonna get now here 3 minus square root 13 now divided by 2. So now this is exactly the bronze ratio. No, it's conjugate. Sorry, this is its conjugate. Conjugate of the bronze ratio with, of course, n equal to 3. Next, this relation is verified, and you can prove this one, the second. And to prove the second, we are going to use z here, z which is equal to this value, product negative x times the conjugate of the bronze ratio. Okay, so how to prove this relation? So proof. So we're gonna have L equal to x 3 times. So the length is this length from here 3 times up to here. We have 3x plus z. Okay, this now z you have it there, so it is 3x minus x times 3 minus the square root 13 over 2. Now, common denominator, we bring 6x minus 3x, now plus square root of 13 times x. Now, in this case, again, we have a difference 3x plus x square root 13 over 2. Now I can factor x out and get 3 plus 13 square root 13 over 2. And what is this? This is exactly mu n positive. So which is the bronze ratio with n equal to 3. And now we've come to the end of this proof. Now what is left? So we have proven that if we take this ratio, we take this length, we divide by the width, which is x, exactly we get the metallic ratio. Okay, now next we can prove that this small rectangular here, this small rectangle, we can also prove that it is a bronze rectangle also. So this will serve as z. Okay, so which is okay. Let me just write it over here. Okay, so next, so I have here I have this becomes a new width. Let us call it W1. This is L1, and we are proving that L1 divided by W1, it's going to be equal to the bronze ratio, the conjugate of this one, and it is going to be equal to, okay, it's going to be equal to L1 is x, so divide negative x, 3 square root 13 over 2. Okay, so now this is it. Simplification, this is 1 over negative 3 minus square root 3, 13 over 2. Now this is 2, negative 2 over 3 minus square root 1, 3. So now this is, if I multiply by the conjugate, 3 plus square root 13, conjugate of the denominator. So what do I get here? So numerator, I have to get negative 2, 3 plus square root 13 over, now this is the 3 power 2 minus 13 square root power 2. So this is negative 2. Now we have 3 plus square root 13 over, now 9 minus 13. So this is going to be equal to negative 4. The numerator have negative 2, which needs some simplification in order to get 3 square root 13 over 2. So now this is exactly the bronze ratio with n equal to 3. Okay, so now which means, in other words, that by this definition, so this is also this small rectangle here is also bronze rectangle, as well as the big rectangle here. Okay, so now let us see generalization in case of n. Similar proof. Have a similar proof exactly. So which is general case. So we use the same procedure to construct the first square, second square, and so on and so forth. Okay, so suppose you have n squares concatenated all together. So now we get half of this length, a half of it, suppose here, and then there. This is nx over 2, nx over 2. And then from the middle on this direction, so from the middle we draw some diagonal, which somehow will meet if we take a projection of this middle point on this vertex of this last square. So we can make a rotation of this point until this direction, and then we raise it up to get the this one. It will be a metallic rectangle, and in order to prove this, we get this length till here, we call it L, and we are going to prove that it is going to be equal to x times the golden the metallic ratio. In addition, since we are calling this one as also this rectangle also is a metallic rectangle, we call this width number 1, new width, and the new length, which is x, of course, same as this. And we prove that this new width is going to be negative x, the conjugate of the metallic ratio. So we need to prove this in order to conclude that we have constructed we have constructed a metallic rectangle. Okay, so first of all, as we did before, let us calculate z, prove that is equal to this. And it is this diagonal minus this length nx over 2. So diagonal minus nx over 2. So diagonal here is by Pythagorean theorem is nx over 2 power 2 plus x square. So square root of it, then minus nx over 2. So this is how we're gonna get z. So it's going to be, so similarly we can factor out x square, it becomes x, then what is left is n square root of n square plus 4 divided by 4. So outside we're gonna have to divide by 2. So this is what we have in this case. So minus n x over 2. So this will become, I can factor out x, and I remain with half of square root n square plus 4 minus n over 2. N over 2. So now this is exactly opposite of the conjugate of the metallic ratio. This is negative x mu n negative. Okay, this is the end of the proof that z is a multiple of opposite of the metallic conjugate. Okay, now length. Let us prove also this identity, and we need to take all these squares, we add z. So all these squares we have n times x times x, so plus z. So that's gonna be nx minus x mu n negative. So this is x n minus mu negative n negative. So this difference is clearly the metallic ratio, because we have n minus half of n plus square root n square plus 4, and this is x times z twice n over 2 minus n plus square root n square plus 4 over 2. So taking this difference is gonna give x something over 2, and which that thing n minus n gonna cancel to 1 n. Okay, now minus here square root n square plus okay, wait, we have to add, and when we add, yes, of course it is this one. Okay, let us see. When we add, there is a mistake here, because this one should be negative. Okay, so if it is negative, here we have negative, we're gonna have positive. Okay, so now what we get here exactly as I told you, as you can see, so it is exactly metallic ratio. Okay, so now what we have here, it is L equal to multiple of the metallic ratio, and I will have to divide by this the same factor x. So we are proving that L over width, x divided by width, is the metallic ratio. Okay, so why is this so important? Is that these metallic rectangle, they appear in what is known as spiral or logarithm spiral. You can call it even metallic spiral, as long as these such triangles, such rectangles are involved. So we shall be talking about this logarithm spiral in our video to come. So thank you very much.